by doing them with the graphing calculator, right? So this is, what again reminds us, what, problems 15, 17 from the, hang on a second, I gotta remind myself which one I'm doing here. So this was 15 from 7.4, right? 7.5, yeah, 7.5, okay. So this is number 15 from section 7.5. So if somebody tunes in later, they'll know what we're doing here. Okay, so they asked you to put these in originally. What they wanted you to do was do them, load the left-hand side in Y1, the right-hand side in Y2, find out what the intersection point was, and you're off to the races, right? Well, the other way you can do them is you can do them using the logarithm. So you can go logarithm, yeah, hang on a sec. I'm gonna do it a little differently. I'm changing my mind. Sorry about that.
Okay.
We can use basically the definition of the logarithm here, and what I mean by that is that you know that on this one in particular, that the exponent on a 2 that gets me 12 is x. Okay. So that's how you switch out of an exponential into a logarithm. It's the whole, the purple math thing that we did, I think it was last week,
yep.
where if you have log base b of x is equal to y, then what that meant was, that's exactly synonymous with saying that the exponent on a b that gets you x is y, all right? That's how you transfer them back and forth. Okay, so that's all we've done here is we've just come in and taken it out of the exponential form and put it into the logarithmic form, which is their inverse operations to each other. But now how do I evaluate this? I mean, how do I get this part over here evaluated? And the way you do that is with the change of base theorem. I mean, the newer TI calculators actually have it built into it, but the way they show in the book is for anybody. So if you've got an old dog TI-83, it'll still work, all right? And so the way it goes is this, is that you use your log key, your base 10 key. So it's logarithm base 10 of 12 divided by logarithm base 10 of 2, and that'll be equal to x. So that's how you actually evaluate that logarithm. So let me get my calculator up here and I'll show you that. So I got to move us out of the way here. Too many windows. I guess I do need my second monitor. Okay, so can you see my calculator okay?
Yes, I can see it.
Okay, cool. All right, so if we do it the way that they said to do it in the book by doing the graphical method, then that's going to be 2 raised to the x goes in y1, and then in y2 you would put in 12. And then go ahead, and I know I'm going to have to do a little bit of adjustment on the windows here, so I'm going to go ahead and do it right away. I'm going to have to make my y max, it's going to have to be bigger than 12 because that's going to be a horizontal line, y equal to 12. So let's make that 15. Let's try that for starts. Let's see what we get here. Okay, there we go. So that point of intersection right there is our solution. So if we go second calc number 5 for intersection, and we go first curve, second curve, scroll over for best guess, it looks like it's at about 3.5849625. That's doing the graphical way, right?
Yep.
Okay. All right, so now algebraically, let's get out of here. We just saw that the answer is logarithm base 10 of 12 divided by logarithm base 10 of 2. So let's check that. So we're going to go logarithm of 12 divided by logarithm of 2. Oh, look at that. The exact same number. That's the same thing we just got a minute ago from the graphical part, right? It turns out that the last place that the cursor was at on the graph gets stored into X. So if I hit X and I hit enter, that's the number that we got from using the graph.
Oh, well, I didn't know that.
Man, I've been working with these silly calculators for much too long. Okay, so is that making sense? So that's the main tool is the change of base theorem. That's the thing that got us from, if you're over here, that's the thing that got us from changing out of exponential into logarithm into something that we could actually do on everybody's calculator, even a TI-83, old dog beater TI. In fact, you can do this on a non-graphing calculator because almost all scientific calculators have logarithm base 10 and logarithm base e built into them. So we're going to do a couple more of them just to see it.
Well, actually, there's the one on 16D that's a little bit more complicated.
Okay, let's go grab that one. Okay, so 16, A, B, C, D. That guy right there?
Yep.
All right. Okay, so I'm gonna clear this screen. And let's put that one in. So this is 16D, right?
Yep.
Was this a media example or what was this one?
No, that one's the practice example.
Okay, so 16D.
The regular section.
Okay, so it's still 3.5, right? Or 7.2.
Yeah. 7.5.
Okay, so the idea, and this is very similar to those previous ones on 15 too, is that you've got to get the exponential isolated first. Otherwise, you can't use that definition that we did to get it out of an exponential and into a logarithm. So this is 4 to the 2x is equal to 68 minus 5, which is going to be 63. So all I did there is just subtract 5 from both sides.
Yep.
Okay, so now I get to use the definition of the logarithm, and that says that the exponent on a base 4 that gets me 63 is equal to 2x. So far, so good?
So far, so good.
Okay, cool. All right, now we're trying to solve for x, so we're going to go ahead and get that 2 out of there. I could divide both sides by 2, but we're going to find that it's going to be much handier in this particular case to multiply both sides by 1/2. So I multiply this side by 1/2, and I multiply this side over here by 1/2, and what happens is those become 1s, right?
Yep.
Okay, cool. So now we got x by itself. So I got 1/2 logarithm base 4 of 63 is equal to x. So I haven't stated the change of base theorem, so let me take a moment and just state that. And what the change of base theorem says is this, is that if you have logarithm base b of a, that's going to be equal to logarithm base 10 of a divided by logarithm base 10 of b. Or, if you prefer, it doesn't really matter which logarithm you use. You can also use the natural logarithm. You can say it's ln of a divided by ln of b. And I got to tell you, I generally use the natural logarithm because I'm lazy because I only have to write down 2 letters instead of 3. So, easy way to remember this, I mean, it's easy, but it's helpful, I think, is that you notice that this is the subscript, so it's down below, isn't it, right?
Yeah.
And this one's up on the top, so it's up here, isn't it?
Correct.
So this guy goes in the top, and this one goes in the bottom, and it's hopefully pretty straightforward to remember it. All right, so back at the ranch here, so then that's 1/2 log of 63 divided by log of 4 is equal to x. And so that's the algebraic solution right there. You can do it graphically and get a decimal approximation, or you can plug that into your calculator and get the decimal approximation.
What I plugged into my calculator, and I didn't know if it was correct or not, is I did the log 63 over the log 4 and divided all of that by the 2 to single out the x.
That's the same thing as multiplying by 1/2, and it would totally work.
Okay.
That's identical, yeah. I mean, if I did it like this, or if I wrote it like this, if I wrote it as log 63 over log of 4 all over 2, that's right, but oh my God, is that ugly? It's true, it's right though, it's not a problem, okay? Is that what you wrote, Charlotte?
That's what I do because I'm not a calculator all day long, so.
Yeah, either way, it doesn't matter. If that's perfectly acceptable.
Okay.
Doesn't matter with that. Okay, got any more for me? Did you got to the discussion question yet?
I have not, because I've been working overtime, but
Okay. Well, if you want to see a little something, there's something I got to do on I kind of promised Alicia that I would look. People have been struggling with the last question on the discussion question, so I said I would probably give some hints on that. So even though you haven't looked at it yet, it's not very dissimilar from what we're doing right now. So
okay.
So that shouldn't be too tough. So let's go open that up. Let's go get that thing open.
While you're opening that up, I'm getting my scratch paper.
Yeah, no problem. Okay, you let me know when you're ready.
I'm ready.
Okay, cool. All right, so question 4 has to do with the Fukushima disaster. So that's a picture of the radioactive plume coming out of, that's Japan right there. That's the plume of ocean water that came out of the Fukushima reactor. All the nasty, toxic, radioactive spillage that was coming out of it. So the following 2 questions are extensions of the previous tabs. To answer these, assume that you're going to be working with this model. It turns out this model right here is really commonly used in all sorts of real-world phenomena: radioactive decay, population growth, spread of rumors, all sorts of things. They use base E, and R is actually the growth rate. That's your old pal, the growth rate in that exponential function. And the inverse function to that is the natural logarithm. It's just logarithm base E. So they ask you, they say, given the half-life is 30.175 years, find the function which gives cesium-137 grams T years later, okay? So how do we do that? So let me go over to the whiteboard for a moment here. So the model that we're working with is P of T is equal to P sub 0 e to the RT. And so the hit list here is that P of T, what that is, that's the population, the percentage, how much you've got. That's the amount at time t. And that could be, grams, could be giraffes, it could be, whatever. It's whatever pertains to the problem you're working with. So that's, give me the time, put it into here, and I can tell you back how many you got. So of course, t, that's just equal to time. Most times it's in years, but it can be in any sort of denomination or units of time that are necessary for your problem. The P sub 0, that's the initial amount. That's what you started off with. It's very similar to when we were working in our book. That's the A. That's the initial amount you started off with. That's at time 0. How much have you got? And so that's why this little sub 0 here, that's delineating that that's at t equal to 0. And then R, that's equal to your growth rate or decay rate, depending. So that's growth or decay rate. And so when you're working with this model, unlike when we were working with the exponentials before, it's whether that number is positive or negative determines whether you have growth or decay. So when R is greater than 0, then you have a growth model. And when R is less than 0, you have a decay model. And then last but not least, E, that's Euler's constant. It's just a number. So it's approximately 2.17178 ... So that's just a number, okay? All right, so back to the problem at hand here. So do this one more time so I get to the right place at the right time. Okay. So they ask us, given the half-life is 30.17 years, find a function that gives the amount of cesium-137 in grams T years later. Okay, so they're asking for the half-life, and we've talked a bit about this, that what we know is that if you're talking half-life, then you don't really need to know what the current amount is, and you don't really need to know what the initial amount is, because half-life infers to you that it's 1/2 of the initial amount that you started off with, right? In other words, 1/2 your initial amount was what you want to know. How much is that at time t? So if you come over here and just plug that into the model, half of p sub 0 is equal to your p sub t, that's equal to your p sub 0 e to the rt. In other words, I want to know half of what I started with. So what that means is that the p sub 0's drop out, and you get 1/2 is equal to e to the rt. And that's true of any exponential model, that the initial amount is going to go away. If you think about those problems that we did in the previous section, that happened every time. The doubling or the half-lives, every time you did it, it always turned out either to be a 2 or a 1/2 over on the left-hand side. Okay, now there's one other really important piece of information that they gave us here. And they told us the half-life. And you can always look this up, like Wikipedia's got for every radioactive isotope you ever want to talk about. They've got the half-life in years. So it's 30.17 years. So when t is equal to 30.17, p of t is equal to 1/2 of p sub 0. So taking that into account back up here in the model that we were just working in, that means that 1/2 is equal to e times 30.17. Okay, now there's another way. Let me do a new screen here. I just want to do this problem one more time, just a slightly different way. There's another way of looking at it. So you could have said, okay, they gave me the time. They said the time was equal to 30.17. And so P of 30.17, plugging that into my model, is equal to P sub 0 e to the r times 30.17, because that is what t is equal to, right? But we also know from what was just given to us and from our previous discussion that we just did is that P of 30.17 is equal to half the initial amount, half of P sub 0. So half of P sub 0 is equal to P sub 0 e to the r times 30.17. And then divide out both sides by P sub 0. That drops out, and you get 1/2 is equal to, that's an e, times r to the 30.17. And I got to admit, when I took this class, I always did that. I went through this, what I'm showing you on this board every time, because it just made it make more sense to me. So you can do it either way. You can just recognize that you're talking about half-life, and so you're always going to have that 1/2 over there, or you can go through the work that I just did and get it to this point. Okay, now, where are we? Well, we have an exponential equation that we need to solve for r. So we're going to use the definition of the logarithm. Now, we have two logarithms on our calculator. We've got logarithm of x. That one is equal to logarithm base 10 of x. And there's another logarithm key in our calculator, ln of x. And that one is equal to logarithm base e of x. So the easiest way to do this problem is just use the inverse operation to logarithm base e, which is ln. In other words, ln of 1/2 is equal to r times 30.17. So that's how I get out of the exponential form and into the logarithmic form. If I was to read this, the way this is read is that the exponent on a base e that gets me 1/2 is equal to r times 30.17. All right, so we're going to divide out that 30.17 from both sides. And that's equal to r. So that's the decay rate for our exponential function. So at this point, we gotta go get our calculator. And so we come over to the calculator, we take the natural logarithm of 1/2, and we divide that by 30.17. And that's what r is equal to. So r is negative 0.02297. And I don't remember. I gotta go back and look quick how many decimal places they tell us to take R out to, but you want to take it out pretty far. These models are very sensitive to small changes in this number make a big difference in the model. So we tend to try and carry it out to like 4 or 5 places. So all of that finally gets us the first thing, the first bullet point is that P of T is equal to P sub 0 e to the negative 0.02297 T. So that's the exponential model that describes the decay of cesium-137, which happened to be one of the nasty isotopes that came out of the Fukushima reactor. So second question is, assuming the amount of cesium-137 was 7,400 times larger than the background level, in other words, there's a background level of cesium-137 that's out there that they say, you know, you can't get away from it anyway, so we'll just call that safe. And let's say that the amount that was coming out of it was 7,400 times larger than that. How long until the fish caught are safe to eat? So what happened is the folks who were monitoring the ocean water right off of the reactor, the fish were coming out having 7,400 times more cesium-137 in them than was allowable. So they didn't give us the amount of cesium-137. They just said it's 7,400 times larger than the background level. So let's go ahead and do that one. So what that says is they want to know is that T is equal to what? That's the question. When P of T is equal to 7,400 times P sub 0. And so the idea is that it's 7,400 times P sub 0, where P sub 0 is the background amount. That's the safe amount, where in this case, P sub 0 is the background amount. Okay, so what that would say if we set up the model again here, so that's what we've got P of T is equal to P sub 0 e to the negative 0.0, let's see, what was it, 2297.
Yeah.
All right, so what we need to do is we need to this time find T. We're trying to find the time until we get back to, you know, the background level. So that says that right now what you've got is 74. Hang on a second. I want to make sure I'm doing this right. I remember something here. Hang on, Charlotte. I'm just having a moment. I got to make sure I'm doing this correct. The P of T is currently equal to that. My bad. Plugging in the wrong spot here. Hang on just a second. It's not P of T is equal to 7,500 or 7,400 P sub 0. Hang on to that. That idea was wrong. I apologize for saying that wrong, but I just remembered it. So this is what is the initial amount. And what we want this to do, we want this to decay back to P sub 0, where P sub 0 is the initial amount. So we want P of T to be equal to P sub 0. In other words, we want P of T to go back, decay back to the background amount again. We don't want P of T to grow up to 7,400 times P sub 0. That would be wrong. That's saying we want it to increase the amount of cesium-137, and that doesn't make any sense. We want the amount of cesium-137 to decay back to the background amount again. So what that says is that P sub 0 here is going to be equal to, and the initial amount, the amount that we're starting with at the moment, is 7,400 P sub 0 times e to the negative 0.02297 T. Sorry about that. I didn't mean to. I know what it's supposed to come out to, and that wasn't going to work. All right, so let's go ahead and divide both sides by 7,400 P sub 0. And if we do that, we get 1 over 7,400 is equal to e to the negative 0.02297t. Okay, so cool. So now what we're going to do is, again, we're going to use our friend, the natural logarithm, to solve this. So that's ln of 1 over 7,400 is equal to negative 0.02297t. Okay, so divide out both sides by that negative 0.02297, and we get ln of 1 over 7,400 divided by negative 0.02297 is equal to how many years it's going to take until the fish are safe to eat. All right, so now what we're going to do is going to get our calculator out. We're going to do that on the calculator. In other words, that part gets done on this bad boy. Let me move it over here so we can see. See what we're doing on the calculation here. Okay, there we go. All right, so it's going to be ln of 1 divided by 7,400 times over the legal limit divided by negative 0.02297. Yeah, it's going to take about 388 years before you can eat that fish. So I'm suggesting that we probably shouldn't eat them, period.
Yeah, no.
Anything that was caught off of that, you have to pretty much, you know. It's,
No sushi.
yeah, not going to ever be edible. So, all right, so that was the question from a bunch of people that posted on the Q&A forum. So I wanted to make sure I got that one in on the tape tonight. Okay. So any other ones I can do for you, Charlotte? Did you got questions on?
That was it. The other one I questioned, the Q&A kind of answered it, made sure that I was getting the same that everybody else was, the exact same, but I kind of knew why. But with the interest,
Oh, okay.
with the doubling, because it's not compounded, it's straight.
Okay.
So that one I figured out. But
Okay,
that
great.
would be it.
Sweet. Okay, well, I'm going to go ahead and log off then.
That sounds good.
It's just you and I again, and then I'm going to go ahead and I'll try and get this posted this evening. So if you need to go back and look at it, you can take a look at it again.
Okay, thank you.
You're welcome. You have a great evening.
You too.